So I'm part of the RSS official statistics section, and I joined early in the year as secretary. So that in my role with the committee, I'm putting this chat on and I've invited a couple of people along to talk. So just a quick bit of housekeeping. So all participants, apart from speakers, will be muted during the webinar. Questions can be submitted at any time by the chat. Please put question at the start of your message, and if there's a specific speaker who you'd like to direct it at. Questions will be answered by the presenters at the end or by their colleagues in the chat if it's appropriate. We ask you to refrain from taking photos or screenshots during the webinar, and a recording of the session will be available for a limited period afterwards. So, introductions to the speakers. So we've got Laura Kristen and Ahmet Aydin from ONS, and they're going to talk about using web scrape data to derive a clothing price index. So, over to you guys. Would you like to take control and bring up your slides?
My name's Laura. I'm from the Office of National Statistics and I'm data science in one of the research teams at the ONS. And today with my colleague Ahmet, we're going to be talking about using web scrape data to derive a clothing price index. So if we can go to the next slide, please. So just to set up really the project we're going to be talking about today, the web scraping project is part of a wider programme of transformation of consumer price statistics in the UK. So our aim is to bring in new data sources for different areas of the inflation basket and eventually transform CPI and CPIH. So the data sources that we're mainly looking at are web scraped and scanner data. So web scraped data coming from websites and scanner data the retailers provide to us from what goes through the till. And what kind of Ahmet and I's job is to research methodologies to most effectively incorporate that new data source into what we're doing at the moment. So it's not looking to necessarily replace our traditional methods at the moment. It's very much looking to improve our coverage of the market. So hopefully resulting in improved accuracy, efficacy and representativeness of consumer price inflation statistics. And today we're going to be talking about one example of the possible application of web scraping, which is still in its very early stages, which is to do with clothing. And just a disclaimer at the bottom there that any results or indices that we're showing you today are very much experimental. So it's very much research that we're carrying out at the moment. So it's not an indication of kind of the clothing market and trends. So if we can go to the next slide, please. So using web scrape data for clothing has advantages and challenges. And one of the reasons actually that we're looking into clothing is that it's one of the most challenging areas in terms of the data that we can get. But there are advantages. So web scrape data allows us to have much wider coverage than before. Our traditional methods take a sample of products, but actually using web scrape data enables us to get many, many more products, many more retailers. So we cover at the moment 17 retailers, 1,000 brands, and our data set dates from June 2020, so roughly 3 years worth of data. Because the data is much wider coverage, it's also much more granular, so we can scrape the data daily. And that amounts to over 900,000 products per month that we can scrape in the clothing market compared to 20,000 with traditional methods. But it does come with challenges in that the data that we receive is very messy. So as you can imagine, 17 different retailers with lots of different clothing products in, there's no standardization of the data we receive as there is in traditional methods. If you think about when you go online to buy a t-shirt from a retailer, you might, in one place you might go, women's tops t-shirts, in another you might go to women's summer. There's lots of different ways that you can get to different pages. The product descriptions will be different, the product names will be different. And because we pull information from lots of areas of the website, it also means that we have lots and lots of different things to try and standardize. So if we go to the next slide, what we have at the moment are 3 key pipelines, and this is also going to form the structure of the presentation today. So I'm going to talk to you first about our clothing classification pipeline, which takes the raw web scrape data, uses a supervised machine learning approach to then classify that data into consumption segments, and I'll talk a bit more about what they are in the next slide. And then I'm going to pass over to Ahmet, who's going to talk about product grouping and the index run, which are later two pipelines. So product grouping takes those classified products from the first pipeline, groups them into groups of similar products with similar prices, and tracks the price of those products over time. And then the index run is what we use to finally produce the indices. So to start talking about classification, and first what I'm going to talk about is consumption segments and what I mean when I say consumption segments. So there is an international hierarchy of kind of clothing classification called COICOP, but it's a very high level hierarchy. So the lowest level of it is women's garments. We classify our data into smaller, more granular segments called consumption segments, which are UK specific. And there are three criteria that we aim to hit with these consumption segments. The first one is that they must be relatively homogeneous. So that just means that they must be similar products with similar price in each consumption segment. They must be simple enough to classify. And that means that not only must it be fairly obvious what each one refers to. So for example, that women's formal blouses there, it's quite hard to decide what's formal, what's not, it's quite subjective. But we also have to have the data that we need to be able to classify things. So for example, if we wanted to classify corduroy trousers and we don't have material as a feature, then that's not simple to classify because we don't actually have the data available to do so. So they must be simple enough to classify, and then finally they've got to be of the right size to produce reliable statistics. And this diagram on the right hand side here visualizes that hopefully in a bit of a clearer way. So women's garments at the top there, if we think about the three criteria on the left, simple enough to classify because most websites state what is women's, what is men's, large enough size to produce reliable statistics, but actually you can have a massive variety of products in there. So from a pair of socks to maybe a sports bra to a t-shirt to a prom dress. So it's going to be loads and loads of different products in there. It's not going to be a particularly homogeneous segment. So then we decided to kind of narrow that down into smaller segments. So something like women's tops, a little bit more homogeneous, still simple enough to classify, still of quite a big segment size. But if you then try and narrow that down further to something like women's formal blouses, yes, everything in there is going to be very similar, very homogeneous, but actually it's going to be quite tricky to classify. It's also going to be quite a small size, so we might not necessarily get as reliable a statistic as we'd like from it. So that's the balance that we're trying to find when we are defining these consumption segments. We can go to the next slide, please, and I'll talk a little bit about labels. So I mentioned earlier on that we're using a supervised machine learning approach. What that means is that we need to teach the machine before it can actually classify something. So it requires a large labeled data set to be able to be trained on, and then we have another data set which it uses what it's learned in that training data set and uses that to label the new one. So the labels are essentially what we're trying to predict. And I've put there, we know what a t-shirt is, the machine doesn't. So basically we need to tell the machine, this is what a t-shirt looks like, and then it can use that, what it's learned there, to then go and classify t-shirts on new data. And in order to do that, we used an in-house app, which several members of our team used to help produce the labeled data set and labeled products across multiple levels of granularity. So the app will go product by product, give us loads of information about it. You can see some examples there. So the category, where the product is found on the website, the product name, the retailer, a few more things that are cut off by that screenshot. And then the labelers, so just people in the prices team, will go through and say that is boys, jumpers, hoodie, etc., multiple levels of granularity. We go to the next slide, please. And you might think that producing a labeled data set in that way is potentially subject to bias, and you'd be correct, because humans, when we label things, humans are subjective. Some of the things, I put the example there of a sweater. Is that a sweatshirt? Is that a jumper? what people classify that as might vary from person to person. So in order to be able to try and measure that, the consistency of labeling, we performed an experiment, starting with a smaller experiment. So 12 labelers labeled around 300 products, but we eventually expanded that to label 30,000 products twice. And then we were able to calculate consistency by calculating the number of products labeled the same divided by the overall number of products labeled. And you've got some results on the right hand side there. So on the x-axis, we have the consistency, so the number of products labeled divided by the number of labeled the same divided by the number of products. And then on the y-axis, you've got the performance of the machine learning algorithm on the test data set. And you can see that there is a positive correlation there. So the more consistent that the human labelers are, the better the classification model can perform. And what we also found, or that is also useful about this experiment, is that it does provide a bit of a benchmark for how we can expect the machine to perform. So we overall found that we had 89% consistency across labelers, and we can now use that as a benchmark for the machine. When it's classifying things, we can expect it to label things with at least 89% accuracy. So move to the next slide. In order to define the labels, we also need to define our features. So the labels are what we're trying to predict. The features are the input variables that we're using to do that. So for example, if you're trying to predict whether something's a t-shirt or not, you might look at whether it is short-sleeved, you might look at its neckline, you might look at its material, for example, and all those things will help the machine to predict what group it belongs to. And we used a combination of methods to create these features. We didn't tell the machine what they were, we asked them to do it themselves. So firstly, we used text mining to indicate some of the kind of bigger or more obvious features, so things like gender and age. So we told the machine to actively look for things like men's, women's, boys, girls, and ages as well, specifically on children's clothing, so that we can split out babies if it says, you know, up to 18 months, whatever, or 6 to 7 years, I don't know. So we used text mining to try and obtain features related to gender and age. And then we also used a method of natural language processing called fast text. And what this is a word vectorization model, which uses product name and product location. So product name just being the name of the product on the website, the location being kind of what the hierarchy is of how you get there. So if you go through men's, jeans, etc. And then it constructed word vectors based on words and n-grams. And n-grams here essentially mean a kind of a number of letters that it groups together. So if you use a bigram, which means two letters, for example, for the word product, you would have PR, RO, OD, DU, etc. And what it does is it takes all that information, it constructs vectors, it gives each product kind of a score in a way on different features, and then it plots them across all those dimensions, as you can see on the right hand side there. And you can see on the right hand side that some of the segments are fairly separated. So for example, that kind of dark pink purple at the bottom is socks, that blue at the top is coat. To the human eye, it doesn't look like they're that separated, but that's actually because this graph is only plotting them on 2 dimensions. The algorithm actually had over 600 dimensions that it was able to plot things on. So if we were able to plot them on 600 dimensions, you would see them a lot more separated. But this is only with 2. We can go on to the next slide, please. Now I'm going to talk a bit more about the model that we used. So our preferred classification model is a model called XGBoost. For those of you who aren't familiar with what this is, it is a sequential training of gradient boosted decision trees. What that means is that it starts off with 1, so calculates 1 decision tree, which if you look at the graph on the left hand side, that blue one at the top has high error, so the first iteration. It will then sequentially train another tree, which improves on that previous tree, group those together, train another tree, group those together, and each iteration improves on the previous one. So it kind of groups weaker trees in order to form an overall stronger model. And we chose the XGBoost for 3 main reasons. The first one was that we got it down to an acceptable training time. So some of the other models that we looked at, which I am going to talk about in a couple of slides' time, were very, very slow to be trained. But we got XGBoost down to an acceptable training time once we added GPU support. It produced confidence scores, which again you'll see in a few slides' time are important for some of the model improvements that we're trying to implement. And finally, it had the highest performance metrics of the models that we tested. And if we go into the next slide, I'm going to talk through what those performance metrics are. So this may be familiar to those of you who are familiar with machine learning, but I'm just going to go through and basically describe what each of these performance metrics are. So we use precision, recall, and an F1 score. Precision is a way of measuring how many things that you've classified truly belong in that class. So the example there of precision is 1 is because that model has labeled all of those things in that green circle as women's dresses, and you can see that they clearly are all women's dresses. It may have missed 1 or 2 kind of positive ones that belong in that class, but actually everything that it has identified is truly a women's dress, and so that would be precision of 1. On the other hand, you've got recall. Recall prioritizes capturing more of the correct classifications. So you can see there that it's correctly classified all of the women's dresses, but it's actually let another couple of things sneak in as well, which have been misclassified. And there are different scenarios when you would want to prioritize one over the other. Recall, for example, is more important in things like fraud detection. It's more valuable for a bank to be able to flag every single fraudulent transaction and then maybe falsely flag a couple which are just normal transactions. It's more important for them to do that than it would be to try and flag fewer transactions but possibly miss a few. And for this, I think there's a build on this slide actually, if you could build it up, please. Yeah, for this particular task, we may decide that precision is more important than recall, because if you think about calculating an index based on 6 women's dresses, which are truly women's dresses, so calculating the price index of women's dresses based on that, you're going to get a more valuable estimate than if you calculate a price index based on 7 women's dresses and a pair of socks, because that's going to affect the index quite a lot. So we may decide that we want to prioritize precision over recall. And the way that you can kind of look at these 2 scores together is called the F1 score. So that is just a harmonic mean of the precision and the recall together. You can also adjust the F score to give more weight to either precision or recall. So for example, the F.33 score there will give, I think, 2/3 of the weight to precision and 1/3 to recall. It might be the other way around, but it will, either way, it will prioritize one over the other. So we're also probably going to play around with that a bit more as research continues. So if we go to the next slide. Yeah, so these performance scores that I just talked to were used to compare the performance of multiple machine learning models back in the very early stages. So I've said that the model we're using is XGBoost, but we also looked at random forests, support vector machines, logistic regression, decision trees. I'm not going to go through in detail what each of those are, but you can see on the left-hand side there an example of how they performed across different segments in women's clothing. The decision trees on their own are quite simplistic, and so that's kind of the bottom light green bar there. You can see that it didn't perform as well as the rest of the models, but we actually saw that, especially for classes which were easier to classify, so things like jeans, most of the scores were fairly similar. It was some of the kind of harder to classify classes like sportswear, where we saw the models differ more. And on the right hand side there, you can see that actually where the classification performance is better, so things like jeans, where all of the models are performing relatively similarly and have quite high performance, that's actually the index values that were then produced were less variable. So you can see on the right-hand side there that the index values for all of the different models are pretty similar. If you looked at that graph for sports bottoms, for example, you'd see a lot more variability between the different models because they were less, had lower performance in classification. So higher classification performance reduces the variability in the index values. And if we go on to the next slide, I'll show you some of the individual class performances for the XGBoost. So again, these are experimental results. So it's just looking at this for part of our research. Overall, the XGBoost model gives us an F1 score of 0.85. If you remember when I was talking about consistency earlier, that compares to 0.89 consistency of our human labelers. So there is room for improvement, not only as a benchmark compared to our human labelers, but also in general, we would be hoping to get somewhere in the 90s for our performance. And you can see on the right-hand side there that it really does differ by class. So I've got the top 5 classes in terms of performance and the bottom 5 classes. You see the top ones are ones that are relatively simple even for a human to classify. So jeans on a website, it normally says if something's jeans, same with shirts, same with skirts. The ones where the classifier struggles a little bit more is things like sports tops. If you think of a description of a sports top versus a normal top, there's quite a lot of overlap there, and so we find that the model is getting confused between classes that are somewhat similar. One thing we might look to do is try and combine some classes together to try and improve the overall F1 scores, but that comes with its challenges in terms of making sure, as I said earlier, that consumption segments are homogeneous, of a big enough size, etc. So there is room for improvement in terms of our scores. And if we go on to the next slide, which I think is my last slide, I'm going to talk about one improvement that we've looked at in the form of confidence thresholding. So what this does is defines a prediction probability that is the threshold for allocating a product to a class. So the XGBoost, for each classification that it makes, each prediction that it makes, it spits out a probability score. So it might classify something as women's jeans, and it will say it is 60% confident that that product belongs to that class. It might say it's 80% confident, etc. And what we've looked at doing is setting a threshold for when it actually carries out that allocation. So if we set that at 80%, the machine would only classify things that it was 80% confident belong to that class. Otherwise, it would just say no prediction. And you can see on the right-hand side there some results of different thresholds that we've looked at. So when there's no threshold, the F1 score is 0.85. When we increase the threshold, we see that the F1 score actually decreases, but that is because precision is increasing at the expense of recall. So as the machine is more and more confident in predicting, it's less likely to capture all of the products because it's only allocating things that it's really, really confident in. And as I mentioned earlier, we might decide that this is actually preferable for us, even though the F1 score is going down, because we want to improve precision over recall. And what we might look at doing as well is using that F beta score instead of F1 score, so weighting precision higher than recall, which would then lead to the overall performance score to be better. So I think that is everything I had on classification. I'm going to pass it over now to Ahmet, who's going to talk about product grouping.
Okay, hi everybody. So I'll talk about product grouping and index run to get our final results. So to start with product grouping. So why do we need product grouping? So like the aim of the index is tracking the price, but in clothing sector, we have high product churn. We have high rapid product entry and exit from the market, which creates a big product churn, and this is a significant problem for clothing market. So like in the clothing market, the products get into the market with high price, stay with that price for a couple of months, and before leaving the market, they generally goes to clearance prices and sold with much lower prices, and then exit the market. So it's hard to track price of a single item in a full year. So that's the product churn problem. So to overcome that, we come up with the grouping, and we want to group similar products together to follow the average price of that group through time instead of tracking and failing to track individual items. And with this grouping, the aim is to reduce the impact of product churn on our final index. So how do we form our groups? So we use a rules-based method, and these rules are the keywords we get from each key attribute columns. So the key columns we use in the clothing data are retailer name, brand name, product description, product style, and material. Those 6 columns are our key columns which to get our rules to form our product groups. And from those each column, we mainly get, like in the basic approach, we get n most common words from those each column and create our rules dictionary. Here I will show a simple example of doing that with 3 products, two main attribute columns, product name and material. And also, let's say we get two most common words from each column. So from these 3 products, let's say the 2 most common words for product name are V-neck and maxi, and for material, polyester and cotton. So here we get our rules dictionary, which will help us to form our groups. So after creating that rules dictionary, we go back to the product, our textual data, and flag the words that we have in the rules dictionary on the data and put them in the group identifier and combine them to form our group names. So in this case, with this 3 product example, product 2 and product 3 will be in the same group, which is identified as maxi cotton using our rules dictionary, and we will track, even though we lose one of them in time, we are able to track the average price of that group in time. So this will help us to form our product groups. So, okay, we built our groups, but we need to assess the quality of our groups. And we will use 2 main metrics to do that, homogeneity and match rate. So the aim of our product groups are to group similar products which a consumer will consider to be similar together. And this is the homogeneity. So we want those groups to be homogeneous. And on the other hand, the other aim is to increase the match rate. So we want our groups to survive in time. So we measure that with the match rate. And actually, these 2 measures, these 2 metrics, goes in opposite directions. So if we want to increase the homogeneity, we will do that in the expense of losing from match rate. So the main measure, the main quality metric we are going to use is the product of homogeneity and match rate. So now I will explain those 2 metrics in more detail. Homogeneity mainly measures price similarity within groups. So it will be calculated with this formula. So to explain it more briefly with words, in the denominator, we would have the total price variance in item prices within a month. And in the numerator, we would have the explained price variance by the grouping. So when we have more homogeneous groups, which has like more similar prices within a group, we would have a higher R-squared score. And this R-squared score would be between 0 and 1. So if we put all groups in a single group, all products in a single group, our R-squared measure will be 0 because we are not explaining any price variance by grouping. But on the other far end, if we don't make any grouping, so if we take all products as a single group, those groups will be perfectly homogeneous. So the R-squared for that case will be 1. And in the real calculation, our R-squared measure will be something between 0 and 1. And the match rate will measure the survival rate of our groups from reference period to current month. And we will calculate this like with this formula using in the denominator the total number of products in a specific month. And in the numerator, we would have the number of products from groups present in both reference period and the current month. So this will give us the match rate, in other words, the survival rate of our groups. In this research, in this product grouping research, we mainly use a reference period of 12 months for our grouping. So this will be, in this way, we will be able to capture the seasonality of clothing market. So we will form our base or reference groups using 12 months of data. Then we will assess the success of grouping in each month in the assessment period. And we mainly work with women's dress in this research because like the richness of that consumption, of that specific consumption segment. I was saying like the aim is to improve the grouping quality. So at the beginning we have started with fixed number of rules. So let's say if we do with like 20 rules per column, we were just naively picking our rules using the frequency of the words in the data. So basically, like we would get 20 most common words from each column, and that would be our rules dictionary. And in that case, for women's dress, we were able to get 54% of MARS score. And we wanted to increase our MARS scores by implementing some improvements. So the first improvement was quality adjustment. And with the quality adjustment, we again, using the fixed number of rules, we were able to adjust our rules dictionary based on the importance of the words. So with that improvement, with that quality adjustment, again, with the same number of rules, we were able to increase our MARS score for women's dress up to 65%. And I will explain the details of that method in a minute. And the other improvement we have implemented was the optimization, rules optimization. Instead of implementing fixed number of rules, we were able to optimize the number of rules we want. And we have tried several different methods, and we were able to get up to 80% MARS score for women's dress. So it's a quite significant improvement. So now let me give some details about those methods. First, the quality adjustment. So in the basic approach, as I said, we were just naively taking n most common words from each column and use that as a rules dictionary. But some keywords with less frequency, which fall out of that region, might have much greater importance to distinguish our products and to help us to form better groups. So in order to take that into account, we have implemented hedonic regression. So instead of let's say taking 20 most common words, we take much more, like let's say 100 or 200 or 300 most common words from each column and run a hedonic regression on each column of words. So with the hedonic regression, we were able to quantify the impact of keywords on price, and we can rule out the insignificant words and keep only the words with significant impact. And we can also re-rank the rules dictionary according to the contribution of each word on the price. So this would help us to take into account more important words with less frequency and to include them in the higher position in our rules dictionary. And like the graph here shows that for women's dress, using only 20 rules from each column with and without quality adjustment. So without quality adjustment, we were losing, with the quality adjustment, we mainly gain with the match rate by losing just a little for R squared. And like without quality adjustment, we were losing around 30% of the groups towards the end of the year. but with the quality adjustment, we have better groups, and we were able to keep up to 95% of our groups towards the end of the year, which is a quite significant improvement. But still, there's a limitation or the caveat for this method. We need to manually configure or need to decide the number of words we want to include in the regression. The second main improvement we have done is the optimizing the number of rules. So basically, we want to find the number of rules which maximizes the mark score we get. And we have tried several alternatives, dictionary optimization, list optimization, and retailer by retailer optimization. And I will go over them one by one now. So the first method we tried was the dictionary optimization. So we can do that with or without quality adjustment. So basically, if we want to do if we want to do the quality adjustment, the first step would be to adjust or like re-rank our rules dictionary. And let's say like this is a simple example here. We have like three attribute columns, and we start with like five most common words from each column, and like we get this rules dictionary. So if we want to run our dictionary optimization over this rules dictionary, we will start with a single group for each retailer. This is important here because like we don't want to mix groups across different retailers. That's why we always keep all the retailers in our dictionary, rules dictionary. And like then the first step would be have single groups for each retailer. Then in each iteration, we would add one rule from each column. So let's say we added one rule and we get a mark score of 65%. We added second rule from each dictionary, we get 70%. Added third and 75%. We are increasing our mark score. Then after some point, the mark scores would decrease as we add more words to our dictionary, because like we would have finer product groups, that would be the homogeneity score would be higher, but we would be losing from product match. So let's say we ended up we tried the grouping within that range, and our optimum rules with the highest mark score would be this one with 3 words from each dictionary, each column. So this would be our final rules dictionary, which we are going to use to form our final groups. So when we implement this method to our women's dress data, starting from 1 rule up to like 60 rules, trying with different number of common words for our quality adjustment, we would get this kind of a result. So as you see, the mark score will start increase as we add each word. Then after some point, it will start to decrease because like we will be losing from product match, even though we are gaining from homogeneity. So that way we would get a optimum mark score. But still, there is limitation with this method. We are imposing the same number of rules for each column. So we don't allow different number of rules from each column. Let's say, for example, the description column might have more rich data, might have more important words than the material column, but still we are imposing the same number of rules from each of those columns. So in order to overcome that, we have introduced the list optimization. So basically here we combine again, like we are taking again the same number of most common words from each column, but the key difference here is we combine those words into a single bag of words and run a single hedonic regression on that bag of words to get a single quality adjusted list, which is ranked. And this will capture like the more important words on top And in this way, for example, in our final quality adjusted list, we might have much more rules in description column than the material column, for example. And the rest will be pretty much the same with the previous optimization method. We will start with single group for each retailer and one rule from each from the list in each step, in each iteration, to find the highest Mars score. So when we apply this method to the same data for women's dress, we get a similar kind of picture. But here we have a slightly higher Mars score with list optimization, and the main advantage here is we allow different number of words from different columns. But still, there's a caveat. Again, we again impose the same words, same keywords, or the same model for every retailer. So the wording might be different from one retailer to another, and we might want to have different keywords for different retailers. So that's why we introduced retailer by retailer optimization. It consumes much more time, but gives value to us. So what we do here is we basically run the list optimization, which I explained a minute ago, for each retailer separately. And the other thing is we run this optimization with various number of most common words, and we pick the best performing model for each retailer among those alternatives. And like that gives us the main advantage of having a retailer specific model configuration. So mainly the retailer specific number of most common words. And also another advantage of this method is it allows us to have like different number of words and different set of rules for different retailers. So for example, if you look at the table here, for example, for retailer C, we get the maximum Mars score with 266 rules. On the other hand, for another retailer, let's say retailer I, we get the maximum Mars score with just 26 words. So this gives us an insight about the different structure or different nature of the wording in different retailers. So that's why it's important to use different models or like different configuration for each retailer. So finally, the more important thing is we get better Mars scores at retailer level. Like even though for overall we increase just 1 percentage point for overall Mars score, when we look into details to look at the retailers themselves, for some of them we gain significantly without losing for any retailer. So it's a kind of like Pareto improvement. So that's why this method is our favorite model, and we built our indices for now using this retailer by retailer optimization method. So now I will show you the indices we get using this method. But before that, let's talk about the web scrape data. So web scrape data is dynamic. So it's a quite different nature than the traditional price collection methods. So in the traditional price collection methods, the manual collector would go and like we can make the linkages from relaunches or like changing products in time. But with web scrape data, we have like millions of data points, and it's hard to make that connection. So we are trying to do that with grouping, but still we have some product churn, and we still have some dynamic data, even though we have done our product grouping. So there will be some groups which are disappearing, and there will be some new groups coming into the market within our index period. So to consider that, we would want to use a different index number method. So there are two main types of index number methods: bilateral and multilateral index methods. And like the traditional methods use bilateral methods. So in which, like in fixed base bilateral methods, we mainly compare 2 months. And if we are able to compare the products which are present in both months, if one of them are missing, we get rid of that product completely for that comparison. But on the other hand, multilaterals work within a window, and within that window, those methods are able to use all products available in all months within that window, even though they're disappearing in some months. So that's why we considering the structure of or the nature of the data, dynamic nature of the data, we want to use a multilateral method. So we use a GEX. We use GEX method, GEX index number method, which is a multilateral method, and we can use 2 versions of it: GEX Jevons or GEX Turnquist. So the main difference is between them is GEX Jevons is working without any weights. So normally in web scrape data, we don't have any expenditure or quantity information. That's why, like, the basic usage would be to use GEX Jevons and tracking the group average prices in time with GEX Jevons. But as we have created our groups, we can use GEX Turnquist using the group sizes we have as weights. So here we assume that the larger groups would have much larger share in the clothing market because they would contain much more products. So we can use GEX Turnquist using the group sizes as weights in the method. So I'm not myself a index number expert, but we have some like ongoing research using those multilateral index methods in the consumer price statistics. You can refer to our to ONS webpage to look at those that research. So finally, the indices. To calculate the indices, we first start with calculating the index for each retailer at each consumption segment level. Then we aggregate those retailers to get a single consumption segment level index. And I'll just show you our experimental consumption level indices. Then the next step would be to aggregate consumption segment level indices to get a single online clothing market consumer price index. So before showing the indices, I would just want to say, like, these are just experimental indices, and there's an ongoing research to improve those indices. So as I said, like, we have mainly worked with women's dress data in forming our product groups, but like, due to the flexibility of retailer by retailer optimization, we are able to give that flexibility for different different configurations for different kind of data. So here I just show the indices for three consumption segments, and they are produced using GEX Turnquist and GEX Jevons, as I explained before. And we also have the ungrouped indices, which is just using the same index method but without any grouping. So just treating each product as a single group. So as I said, like, the final step would be to aggregate them to get a single price in the consumer clothing price index. So in conclusion, in this project, we have started with very unstructured, very messy web scrape data, and to use that, like, in this process, to get we have shown the process to get a clothing price index. So initially, we have started to classify that raw data into consumption segment using supervised machine learning. Then we have tried to create homogeneous product groups, which will also survive in time for index purposes. And finally, we calculated a price index using a multilateral method, which is a suitable method for the dynamic structure of the data. So, like, the main advantage, why do we try to do that, is, like, we try to make use of a wide sample of products and we make use the dynamic structure of the data. So we are able to capture a much wider range, and we collect more frequent prices with web scraping compared to manual price collection. And we continue to improve our methods, and the research is ongoing for this clothing project. Thank you very much for listening. Now I think we can take questions.
Thanks, Ahmet and Laura. Yeah, that was great. And we've got no questions in the chat at the minute, but that doesn't mean there isn't any. So if anyone's got any questions, please post them in the chat, or of course, come off mute if you'd like to ask the speakers directly. Maybe whilst people have time to think, I could ask you a question. So I like to think about the higher level details. So one question I was thinking is, if you didn't make all of these improvements, what would be the difference? So essentially, I'm asking, what's the wider impact of this work?
So I can answer that. So like, as I've shown, like these indices, without grouping, we believe that due to the nature of the clothing data, we have high churn, high entry and exit, and it will create a bias in the index. So we want to address that. So normally in manual collection, we are able to make linkages, like when a manual price collection goes into the shop and see that the product they collected last month is not on the shelf anymore. They're able to pick the most, like the closest item to that, and they can make that linkages. But with web scrape data, with like millions of products, we can't do that easily. So that's why we introduce the product grouping. So we want to capture those similarities in homogeneous groups and able to track those prices in time. So we think that we are addressing that bias in the index without any grouping by using these methods.
Thanks, Ahmet. Yeah, that's understandable as well. So thank you.